So in the previous class, the previous two classes I have discussed the term center of mass, position vector of center of mass, and Cartesian coordinates of center of mass, and some special cases in finding the position of center of mass. And I have discussed one problem also. So in this class, I am going to discuss about the velocity of center of mass, acceleration of center of mass, and principle of conservation of linear momentum. So again, going back to the definition of center of mass. Now in this class, now you just concentrate only to listen to me. Just concentrate only to listen to me and keep looking on the screen. Don't write the running notes. When I am discussing, I will be showing you the notes separately. You can copy the notes part later. I will be showing you the type formed or PowerPoint presentation of the notes. Now you just concentrate only to listen to me. If you consider a system of n particles with masses m1, m2, m3, etc. up to mn. If r1 bar is the position vector of the first particle of mass m1 with respect to origin O of a coordinate system, the r2 bar is the position vector of second particle of mass m2, and r3 bar is the position vector of third particle of mass m3, and so on. The same way rn bar is the position vector of the location of the nth particle of mass m1. Then center of mass system of the n particles is defined as a geometrical point whose position vector with respect to same origin O given by RCM bar equal to M1 R1 bar plus M2 R2 bar plus M3 R3 bar, etc. up to Mn Rn bar divided by sum of the masses of all the n particles of system. Now if you differentiate this equation, we can differentiate this equation both sides with respect to time t to get the expression for velocity of center of mass. Therefore, we can write d by dt of, we can differentiate both sides with respect to time t, drcm bar by dt. The masses of the individual particle system can be treated as constants with respect to time, do not change with time in the Newtonian mechanics. So 1 by m1 plus m2 plus m3 up to mn can be treated as a constant factor. You can write m1 into d r1 bar by dt plus m2 into d r2 bar by dt plus m3 into d r3 bar by dt, etc. up to mn into d rn bar by dt. Now rate of change of position vector of the particle with respect to origin O of an inertial frame of reference or coordinate system. This is the velocity vector of the particle with respect to the origin O. So dr1 bar by dt gives the rate of change of position vector of the first particle with respect to the origin O. That gives you the linear velocity vector of the first particle. That means dr R1 bar by dt can be written as V1 bar. V1 bar is the linear velocity vector of the first particle of mass m1. Similarly, dr2 bar by dt can be written as equal to V2 bar, where V2 bar is the linear velocity vector of second particle of mass m2. The same way dr3 bar by dt can be written as equal to V3 bar, where V3 bar is the linear velocity vector of third particle of mass m3. drn bar by dt can be written as equal to Vn bar, which represents the linear velocity vector of the nth particle of mass Mn. Now drCm bar by dt can be written as equal to Vcm bar, V bar subscript Cm, which represents the linear velocity vector center of mass of the system with n particles. drCm bar by dt is the rate of change of position vector center of mass with respect to the origin both. That gives the velocity vector center of mass. So if you make these substitutions, you can get the expression for the velocity center of mass of the system with n particles. So the linear velocity vector of center of mass of the system of the n particles is therefore given by V bar subscript Cm equal to m1 v1 bar plus m2 v2 bar plus m3 v3 bar, etc. up to mn vn bar divided by sum of the mass of all the n particles of system. As you know, product of the mass of the particle and linear velocity vector of the particle is called the linear momentum of the particle, denoted by P bar. So product m1 v1 bar gives you the linear momentum of the first particle of mass m1, denoted by P1 bar. The product m2 v2 bar gives you the linear momentum vector of second particle of mass m2, denoted by P2 bar. The product m3 v3 bar represents the linear momentum vector of the third particle of mass m3, denoted by P3 bar. The product mn vn bar can be written as equal to Pn bar, P bar subscript n, which represents linear momentum vector of the nth particle of mass Mn. Therefore, the velocity of the center of mass system of the n particles can be written as the vector sum of the linear momenta of all the n particles of system divided by the sum of the masses of all the n particles of system. So vector sum of linear momentum of all the n particle system gives you the total linear momentum of system, which may be denoted by capital P bar. So the mass of all the particle system gives the total mass of system, denoted by capital M. So velocity vector center of mass system of the particles equal to vector sum of linear momentum of all the particles of system divided by total mass system. The vector sum of linear momentum of all the particle system denoted by capital P bar. That means capital P bar equal P1 bar plus P2 bar plus P3 bar up to Pn bar. Capital M represents the total mass of system, which is equal to sum of the mass of all the n particle system. So from the last equation you can write capital P bar equal to capital M into VCM bar. That means that vector sum of linear mode of all the particles of system will be equal to product of the total mass of system and velocity center of mass of system. The vector sum of linear mode of all the particles of system we call total linear mode of system. So the total linear mode system of particles will be equal to the product of the total mass system and velocity center of mass system. So total linear mode system of particles with respect to origin O of a coordinate system or reference frame will be equal to product of the total mass of system and velocity center of mass system with respect to same origin O. That means to find the total linear mode system of particles, we can consider the system of particles as equivalent to a single particle whose mass equal to total mass of system, which moves with a velocity equal to the velocity center of mass. Next, I am going to discuss the acceleration of center of mass. So coming to the now acceleration of center of mass. Just concentrate only to listen. Don't write running notes when I am discussing. You can write the notes later. So just before we discuss the velocity center of mass system, then particles is given by VCM bar equal to M1 V1 bar plus M2 V2 bar plus M3 V3 bar, etc. up to Mn Vn bar divided by sum of the masses of all the n particles of system. To get the expression for acceleration center of mass, you can differentiate this equation both sides with respect to time t. When you are differentiating both sides with respect to time t, the masses of individual particles of system can be treated as constants. So dVcm bar by dt can be written as 1 by m1 plus m2 plus m3 etc. up to mn. And at m1 into dv1 bar by dt plus m2 into dv2 bar by dt etc. plus m3 into dv3 bar by dt up to mn into dvn bar by dt. Now rate of change of velocity vector of the particle with respect to origin O gives you the acceleration vector of the particle. So dv1 bar by dt gives you the linear rate of change of velocity of the first particle of mass m1. That will be equal to the linear acceleration vector of m1. That is denoted by a1 bar. So a1 bar represents the linear acceleration vector of the mass m1. The same way dv2 bar by dt can be written as equal to a2 bar. This a2 bar represents the linear acceleration vector of second particle of mass m2. And dv3 bar by dt can be written as a3 bar. a3 bar represents the linear acceleration vector of the third particle of mass m3 and so on. So dvn bar by dt can be written as equal to an bar. So an bar represents the linear acceleration vector of the nth particle of mass mn. So dvcm bar by dt can be written as equal to acm bar. Here A bar subscript Cm represent the linear acceleration vector center of mass to the n particles. So the linear acceleration vector of the center of mass of the system with n particles is given by Acm bar equal to m1 a1 bar plus m2 a2 bar plus m3 a3 bar plus up to mn an bar divided by sum of the masses of all the n particles of system. So this gives you the expression for acceleration center of mass of the n particles. Now from Newton's second law, the product of the mass of the particle and linear acceleration vector of the particle gives you the resultant of all the forces acting on the particle. So product m1 a1 bar can be written as equal to f1 bar. F1 bar is the resultant of all the forces acting on the particle of mass m1. So product m2 a2 bar can be written as equal to f2 bar. F2 bar is the resultant of all the forces acting on the second particle of mass m2. That means F2 bar represents the vector sum of all the forces acting on the mass m2 due to other particles in the system, and also the vector sum of the external forces acting on the particle of mass m2 due to the objects outside system. Similarly, m3 a3 bar can be written as f3 bar. F3 bar is the resultant of all the forces acting on the third particle of mass m3. The same way, mn an bar can be written as fn bar, f bar subscript n, which represents the resultant of all the forces acting on the nth particle of mass m1. So acceleration of center of mass is system of all the particles, vector sum of all the forces acting on all the particles of system divided by sum of the mass of all the particles of system. The vector sum of all the forces acting on all the particles of system can be written as the vector sum of the external forces and vector sum of the internal forces between the particles of system. Here capital M represents sum of the mass of all the particles of system. So here F bar subscript ext represents the vector sum of all the external forces acting on all the particles of system. F bar subscript internal represents the vector sum of all the internal forces between the particles of system. You must be knowing the distinction between external forces and internal forces, which I mentioned in the past in Newton's laws, but still again I tell you, when you consider two or more number of particles as one system, so in general when you consider two or more number of particles as one system, the force exerted or applied on one particle in the system by another particle in the same system is called as internal force. The forces acting on the particle system due to the objects outside system, that means the forces which are exerted on the particles in the system by the objects outside the system, they are called external forces. So F1 bar plus F2 bar plus F3 bar. So acceleration center of mass can be written as M1 F1 bar plus F2 bar plus F3 bar up to Fn bar divided by sum of the mass of all the n particle system. Now F1 bar plus F2 bar plus F3 bar up to Fn bar gives you the vector sum of all the forces acting on all the particles of system. So the vector sum of all the forces acting on all the particles of system is equal to vector sum of the external forces acting on the particles of system and the vector sum of internal forces between the particle system. The internal forces always occur in pairs. Suppose if the force on M1 by M2 denoted by F bar 1 2, then the force on M2 by M1 is denoted by F bar 2 1, and these two forces will be equal in magnitude but opposite in direction. From Newton's third law, F bar 1 2 is negative of F bar 2 1. Therefore, F bar 1 2 plus F bar 2 1 will be equal to 0 bar. In a similar way, in general, if you consider two particles, if M subscript I denotes mass of ith particle and M subscript J represents mass of the jth particle, then force on ith particle by the jth particle denoted by F bar subscript Ij. The force on ith particle by jth particle denoted by F bar subscript Ij. The force on the jth particle by the ith particle that is denoted by F bar subscript Ji. These two forces form action-reaction pair. That means F bar subscript Ji can be written as negative of F bar subscript Ij. So the vector sum of all the internal forces between all the particles of the system will be equal to 0 vector. Therefore, vector sum of all the forces acting on all the particles of system can be simply written as equal to the vector sum of the external forces acting on the system therefore the acceleration of center of mass in system of the n particles can be written as equal to vector sum of all the external forces acting on all the particles of system divided by sum of the masses of all the particles of system. That means in calculation of acceleration center of mass, we have to only find the vector sum or resultant of the external forces acting on the system and divide with total mass system. We need not have to consider, you should not consider the internal forces between the particles of the system in the calculation of the acceleration center of mass. So the acceleration center of mass system of particles, same as the acceleration of single particle, whose mass is equal to total mass of the system. When same external forces applied on the system are also applied on that particle. So remember that center of mass is not a particle. Center of mass represents a geometrical point. The acceleration center of mass system of the particles, same as the acceleration of single point particle, whose mass is equal to the total mass of system. When same external force applied on the system are also applied on that particle. So the vector sum of all the external forces acting on all the particles of a system can be written as the product of total mass of the system and accelerate of center of mass of system. So earlier I told you the vector sum of linear moment of all the particles of system is equal to product of total mass of system and velocity at the center of mass of the system. So center of mass system of particles is a geometrical point which moves in the same way as a single particle whose mass is equal to total mass of the system would move when the same external force applied on the system are also applied on that particle. The motion of whatever system you choose or select in the application of laws of mechanics, in any example, the accelerator center of mass of system depends only on the external force acting on system. The motion of center of mass of any system is only influenced by the external force acting on system. The internal forces between the particles of the system do not play any role in the motion of center of mass of the system. Suppose if the vector sum of all the external forces acting on all the particle system vanishes, that may become 0. And the accelerator center of mass system is 0. The accelerator center of mass system can be the time rate of change of the velocity center of mass of the system, 0. So the accelerator center of mass of system will be 0 and only when the velocity of center of mass of system remains constant. That means if the resultant of all the external forces acting on all the particles of system becomes 0 and the velocity of center of mass of system remains constant both in magnitude and direction. So when the resultant of all the external forces acting on all the particle system becomes 0, then the velocity center of mass system remains constant both in magnitude and direction. That means the velocity center of mass system will not be changed due to the internal force between the particle system. The velocity center of mass changes only due to the external force acting on system. When no net external force acts on system, then the velocity center of mass system remains constant both in magnitude and direction. Now total linear order system is equal to product of the total mass of system and velocity center of mass system. The total mass of system does not change with time. Then total linear amount of system remains constant. If the net external force on the system is 0. So if the mass of the system does not change with time and the velocity center of mass is constant, then we can say the total linear amount of system remains constant. That means if the resultant of all the external forces acting on all the particles of system becomes 0, I mean if no net external force acts on system, then the total linear amount of system remains constant both in magnitude and direction. Here capital P bar represents the total linear amount of system of the particles. That means vector sum of the linear moment of all the particles of system remains constant both in magnitude and direction. If the vector sum of all the external force acting on system becomes 0. This we call principle of conservation of linear momentum. So if the resultant of all the external forces acting on all the particles of system becomes 0, then the vector sum of linear momentum of all the particles of system remains constant both in magnitude and direction. if the total mass of the system does not change with time. This we call principle of conservation of linear momentum. But don't mistake that linear momentum of individual particle system do remain constant when external force on system is zero. The linear momentum of individual particle system may be changed and usually change due to the internal forces between the particles of system. But total linear momentum system of particles or vector sum of linear momentum of all the particles of a system will not be changed due to the internal forces between the particle system. The total linear momentum system changes only due to external force acting on system. So while discussing the examples in center of mass and conservation of linear momentum, you have to keep in mind that the internal forces between the particle system do not play any role in the motion of center of mass of system. The velocity of center of mass of system will be changed only due to the external force acting on system. And we deal only those examples where total mass of system does not vary with time in most of the examples at present. Therefore, total linear momentum system also changes only when velocity of center of mass of system changes. I mean, if the total mass of system is fixed. And with velocity of center of mass system changes only due to external force acting on system. Therefore, the total linear momentum system of particles will be changed only due to external force acting on system. So next I am going to show you the notes for what I have discussed in today's class. Then I am going to show you the PowerPoint presentation of what I have already discussed in today's class. So come on, those who are writing the notes, again get ready with your notebook and pen. So I am going to summarize the discussion, summarize the discussion I have done in the present class. So velocity of center of mass now for system of particles. The position vector of center of mass is given by RCM bar equal M1 R1 bar plus M2 R2 bar plus M3 R3 bar up to Mn Rn bar divided by M1 plus M2 plus M3 up to Mn. So differentiating both sides with respect to time t, you get dRCM bar by dt equal to 1 by M1 plus M2 plus M3 up to Mn whole multiplied by M1 into dR1 bar by dt plus M2 into dR2 bar by dt plus M3 into dR3 bar by dt etc. up to Mn into dR1 bar by dt. Come on, those who are writing the notes, write the equations shown on the screen. In case you need more time to copy the notes, you can take a pause and take your time. I am going to show you the continuation for this. So the linear velocity center of mass system of n particles is given by VCM bar equal to M1 V1 bar plus M2 V2 bar plus M3 V3 bar up to Mn Vn bar divided by M1 plus M2 plus M3 up to Mn. Or you can write VCM bar equal to P1 bar plus P2 bar plus P3 bar up to Pn bar divided by M1 plus M2 plus M3 up to Mn. Or VCM bar equal to P bar by capital M. Come on, finish writing. You write capital P here in the numerator on the right side in the last equation. Come on, copy it on the notes. So next I am going to show the notes continuation to this. In case you need more time to copy the notes, you can take a pause. Where P bar equal to P1 bar plus P2 bar plus P3 bar up to Pn bar. And capital M equal to M1 plus M2 plus M3 up to Mn. So you can write capital P bar equal to capital M into VCM bar. So the vector sum of the linear momentum, linear momenta it should be plural. The vector sum of the linear momenta of all the particle system will be equal to the product of total mass system and velocity center of mass system. Come on, finish writing the notes. In case you need more time to copy the notes, you can take a pause and take your time. Next, you write accelerated center of mass. The system of n particles, velocity center of mass is given by m1 v1 bar plus m2 v2 bar plus m3 v3 bar up to mn vn bar divided by m1 plus m2 plus m3 up to mn. Can differentiate this equation both sides with respect to time t. dVcm bar by dt equal to 1 by m1 plus m2 plus m3 up to mn whole multiplied by m1 into dv1 bar by dt plus m2 into dv2 bar by dt etc. up to mn into dvn bar by dt. Come on, finish writing. So dv1 bar by dt can be written as a1 bar, which is the accelerator of m1. dv2 bar by dt equal to a2 bar. dvn bar by dt equal to an bar. dvcm bar by dt gives you accelerated center of mass denoted by acm bar. So accelerated center of mass system of n particles is given by m1 a1 bar plus m2 a2 bar plus m3 a3 bar up to mn an bar divided by sum of the mass of all the n particles of system. Come on, finish copying this. In case you need more time to copy the notes, you can take a pause and take your time. So the linear accelerator vector of center of mass system of n particles is given by ACM bar equal to F1 bar plus F2 bar plus F3 bar up to Fn bar divided by M1 plus M2 plus M3 up to Mn. As I discussed previously, F1 bar is the resultant of all the forces acting on M1. F2 bar is the resultant of all the forces acting on M2. F3 bar is the resultant of all the forces acting on third particle of mass M3. Fn bar is the resultant of all the forces acting on the nth particle of mass Mn. This you can write R ACM bar equal to F bar ext by capital M, where F bar ext represents the vector sum of all the external force acting on all the particles of the system. Come on, copy down the notes. So I will read out one statement that is shown on the screen here. The center of mass system of particles is a geometrical point which moves in the same way as a single particle whose mass is equal to the total mass of system would move. And the same external force applied on system are also applied on that particle. Come on, finish writing the notes. In case you need more time to copy the notes, you can take a pause and take your time. I'm going to show the continuation for this. You can write F bar ext equal to capital M into ACM bar. The vector sum of all the external forces acting on all the particle system will be equal to the product of total mass of system and linear accelerated center of mass of system. So F bar ext is 0 bar, then accelerated center of mass is 0. Or accelerated center of mass is equal to dVcm bar by dt, that will be 0. Come on, finish copying the notes up to here. So in case you need more time to copy the notes, you can take a pause and take your time. I'm going to show the continuation for this. So if accelerated center of mass is 0, velocity center of mass is constant, or VCM bar is constant. So if the magnitude of the vector sum of all the external force acting on a system is 0, the velocity center of mass of system remains constant both in magnitude and direction. The total mass of system does not change with time. Then the total linear amount of system also remains constant both in magnitude and direction when the net external force on the system is 0. Come on, finish copying this. So in case you need more time, To copy this, you can take a pause and take your own time. After copying this, then again you can stop writing the notes. Again you can start concentrating to listen for the continuation. So next I am going to discuss some special cases based on the conservation of momentum. So when the net external force acting on the system is 0, then the velocity center of mass system remains constant both in magnitude and direction. So while discussing numerical problems and examples in this chapter, we come across number of examples where you have system of two particles which move only under the action of mutual internal forces between them. That means if you suppose consider, you now should stop writing the notes, you should concentrate to listen. I will be showing the notes for the special cases later. First you concentrate only to listen. So if you consider the system of two bodies, or even if you consider one rigid body of mass m1, another rigid body of mass m2, the rigid body of mass m1 can be treated like a point mass m1 located at the position of its center of mass. The second body of mass m2 can be treated as a point mass m2 located at the position of its center of mass if each body is performing pure translatory motion. That means if only unbalanced force acting on m1 is the force on m1 by m2. Only unbalanced force acting on m2 is the force on m2 by m1. Let us consider system of two particles which move only under the action of mutual internal forces between them, such that no external force act on system. Let us suppose the two particles are initially at rest, so that initial velocity of each particle is 0, initial momentum of each particle is 0. If no external forces act on the system, or if resultant of all the external force acting on the system is 0, then total momentum system remains constant. So vector sum of final momentum of system will be equal to vector sum of initial momentum of the system. Pi bar is the initial momentum of system of the two particles. Pf bar is the final momentum system of the two particles. That each particle is initial at rest, then initial momentum of each particle is 0. Final momentum of the two particles at a later instant will be the vector sum of linear momenta of the two particles. That means at any later instant, the two particles will be moving in opposite directions with the same magnitude of linear momentum. The two particles moving in opposite directions, same magnitude of linear momentum. So mod of P2 bar is same as mod of P1 bar, that can be denoted by P. So you can compare the kinetic energies of the particles. Remember that the internal forces between the particle system cannot change the total linear momentum system, but internal forces can change the total kinetic energy system. So initial kinetic energy of the first particle of mass m1 at a later instant during the motion, you can write p square by 2m1. Kinetic energy of the second particle of mass m2 can write p square by 2m2. That means ratio of the kinetic energies of the two particles at a later instant before they collide with each other, when they move only under the action of mutual internal forces, will be equal to inverse ratio of their masses. Let small r denote the initial distance between the two point mass m1 and m2 when they are initially at rest. Now, when you consider a system of two particles, If no external force acts on system, velocity center of mass system remains constant. The resultant of all the external force acting on system is the velocity center of mass system remains constant. That means the final velocity center of mass at later instant will be same as the initial velocity center of mass. If each particle is initial at rest, initial velocity of each particle is 0, initial velocity center of mass system is 0. If initial velocity center of mass of system is 0 and velocity center of mass system remains constant during subsequent motion of the two particles under action of mutual internal force, so velocity center of mass will be 0. That means center of mass system of the two particles will be at rest. The center of mass system of the two particles is at rest. The position vector of center of mass of the system of the two particles with respect to a fixed origin O will be constant. So position vector of center of mass system at a later instant is equal to the position vector of center of mass system at the earlier instant. Position vector of center of mass system at the earlier instant, you can write m1 r1 bar plus m2 r2 bar by m1 plus m2, where r1 bar is the position vector of initial position of m1, r2 bar is the position vector of initial position of second particle of mass m2. The position vector center of mass of system at later instant, you can write m1 r1 dash bar plus m2 r2 dash bar by m1 plus m2. m1 plus m2 can cancel. Here r1 dash bar is the position vector of final position of first particle of mass m1. r2 dash bar is the position vector of final position of second particle of mass m2. So you can write here m2 into r2 dash bar minus r2 bar equal to minus m1 into r1 dash bar minus r1 bar. As I discussed earlier in vectors, position of a particle changes. That means if Ra bar is the position vector of initial position of a particle and Rf bar is the position vector of final position of the particle, and displacement of the particle in vector form, we write Rf bar minus Ra bar. Here R1 bar is the position vector of initial position of M1. R1 dash bar is the position vector of final position of M1. So R1 dash bar minus R1 bar gives you the displacement vector of M1. R2 dash bar minus R2 bar gives you the displacement vector of M2. So I will continue my discussion in my next class.